Hello and welcome to It Mindsetters. This is your favorite show, your best learning show ever, which is Learn Extra Live with me, Avery. On a Tuesday, I hope you're up and ready to learn more with us. It is springtime, so you don't have any excuse to feel tired, but it is time to learn more with us. I'm joined by Phil. How are you, Phil?
I'm great, thanks, and you?
I'm feeling good, man. I have no excuses and complaints.
Oh, great. That's good to know.
Okay, what are we going over today?
Well, today we're finishing off our section on motion. We're going to be dealing with some of the graphs of motion that we've learned in the previous lessons, and we're going to be talking about the equations of motion, which a lot of people really struggle with.
All right, well, we're here to help you, Mindsetters. If you're struggling, be on Facebook. Our Facebook page is facebook.com/learnextra. Like the page, communicate with us, help other Mindsetters also that are on the page struggling. If you have liked the page, share the page to other guys, some of your schoolmates who might be needing that extra push, because we're here to help you. Otherwise, you can follow us on Twitter at learnextra, and lastly, download our notes all for free on learnextra.co.za/live. They're for free. The first link will also be on Facebook. So let's learn more.
Absolutely, guys. Well, thanks so much for that introduction. Now, this is a third of our series of motion. Now, we're dealing with motion, things which are moving. So, guys, I've talked to you about this before. I just want to get your gears all into action and all joining together. Guys, motion is all about displacement, velocity, and acceleration. So we started dealing with these words. Guys, get on the page with the notes. Absolutely, Avery's now. It's Avery, not Abram.
Yes.
Okay, so we shorten things are nice and fast. Okay, now dealing with motion, we're dealing with displacement, velocity, acceleration. If you're not sure what those words mean, inside the notes I've left a really nice glossary, and just make sure that we re-explain all of these things. Okay, so like I said, motion, chapter 3, now we are dealing with some of the end parts of motion, some of the trickier parts. Now, we're going to be revising as usual. I'm going to be taking you on a little bit of memory lane, and we're going to be dealing with displacement and velocity versus time graphs. Guys, we're going to be just doing a little bit of revision just to make sure that you are on exactly the same page. And then, somewhere towards the middle of the lesson, we're going to be starting to introduce acceleration graphs. Now, that's acceleration versus time. Let me not cross out acceleration. So, there we go. Fantastic. So displacement time graphs and acceleration graphs. Those are going to be really interesting. So now what we're going to do with all of this is I'm going to introduce the equations of motion. And that's going to be right at the end. Equations of motion are the culmination of your entire section. Now, guys, you might say, oh, this is not my favorite, or graphs might not be my favorite thing because in maths I wasn't so great at graphs. Guys, the really nice thing is if you're taking maths and science together, we're going to help each other. It's a great combination. Now, you might say, okay, graphs, equations, oh, this is the stuff that I hate the most. But guys, these are really nice and simple. I'm going to hold your hand as I always do. We're going to guide each other through this, and we're going to help each other, and we're going to learn more and learn extra. So, working with equations of motion is the very last thing. And guys, please don't be scared off by some of the maths type words. We're going to be dealing with them in small pieces. And hey, maybe even we sort out some of your maths problems today. So you should be watching on Mondays and Tuesdays. So maths and science together. Okay. So now let's get started. Let's go through this very, very quickly. I want to do a little bit of revision over these next few minutes over what we were doing last week. And I wanted to talk about some of the words that we were dealing with, and here they are. First of all, here we go, displacement. Displacement is one of the words that we learned about last week. Displacement was a change in position in a particular direction. Now, you might notice that I said, okay, it's a change, which means a number, and a direction. So that made displacement a vector. Now, I used displacement to calculate velocity. So velocity was the rate of change of displacement. So displacement is the movement. Velocity is how quickly I get it done. Now, both of these are referring to time. Now, what we're going to do is we're going to start to discuss different types of motion. We're going to discuss the graphs around them. And eventually, we're going to figure out some shortcuts to be able to figure out, okay, I can use that graph to find that, or I can work backwards from that to that. Now, I'm going to find the relationship between an xt graph and a vt graph. Now, just bear in mind, some of the people that were watching last week said, is it always x? No, guys, it's not always x. X is dealing with horizontal movement. In later years, what you're going to be dealing with is vertical motion as well. Can you think of what I might use in place of x, which is horizontal? Now, if you're starting to think of maths and you're starting to think of if x is horizontal, y must be the vertical. So you can have y versus t if we've got a vertically moving object. So that's a really nice comment from one of our watchers last year. Okay, so now what we're going to do is now we're going to describe different situations, and then we're going to piece it all together. Okay, so my situation, which I would like to graph out. And guys, if you've got the notes, you can draw with us because I've given you all the same graphs, and it's really nice. Avery's going to be posting some of the links, is he?
Yes.
Fantastic. Okay, he's quick on the job, guys. He's got lots of velocity. Okay, so constant velocity, what does that actually mean? Now, first of all, before I even say constant velocity, okay, you can say, oh, the motion is constant. Now, please, please, don't ever talk about the motion. When you talk about motion, we've got these three different words that we use to describe motion: displacement, velocity, and acceleration. Now, I want you to start each one of your sentences using those words. So when I say constant velocity, oh, that means that the velocity does not change as time passes. How I describe my graphs is very important, guys. Make sure that you know which part of the motion you're dealing with. Okay, so let's just draw what I've just described. I said that as time passes, the velocity does not change. So that means that my velocity starts at a certain level and it does not change. So you can see that as time passes, it remains the same value. That's what it means to have a constant velocity. The velocity does not change. That's the meaning of the word constant. Okay, now you might say, oh, well, I'm getting a little confused here. But what you've got to do is you've got to take a look at your graph and you've got to say, what graph am I looking at? What is my axis? So now you might say, well, that's a little bit stupid. It's already written there. But guys, it's not a stupid thing. Ask yourself this question and say, oh, I'm going to read the graph on the right. That is a graph of v versus t. So let's use those words to describe the motion of this object. So I start my sentence with the velocity. So the velocity is at a certain level there. After some time, can you see that nothing changes? So I'm going to move all along here. As time passes, the velocity does not increase or decrease. It doesn't matter where in time it is. So as time passes, the velocity does not change. So that means that I have a constant positive velocity. Now, what does that mean for my displacement? And you might say, okay, well, this car is going straight. Please, guys, don't make the mistake. Graphs are not pictures of the motion. What they do is describe the numbers. They help us see the numbers better. Now, my object doesn't necessarily mean that it's traveling east because it looks like it's sideways. Guys, please don't get them confused. This is just a graph describing velocity as time passes. Now let's turn our attention to our x versus t graph, my displacement time graph. Now I've got to be very careful about this. What I've got to say is, okay, constant velocity, what does that mean? Oh, I need to know my definition. That means that the rate of change of displacement is constant. Now, rate of change, guys, you've heard this in maths before. What is the rate of change? The rate of change is the gradient. So, said in other words, the gradient of my x versus t graph is going to remain constant. So, as time passes, my displacement will increase, but I'm not done yet, at a constant rate. So, there's two parts to the description there. So that means as time passes, the displacement will increase. I know this because I'm moving, but it will increase at a constant rate. So what I'm going to get is this beautiful straight line because that means that the gradient is going to stay the same. Let me just focus on that for a section. Let's just talk about what that actually means, that as time passes, the displacement is increasing at a constant rate. So there's two parts to the description. So I know that displacement will go up. So as time passes, it will go up by the same amount. That's what it means to have constant velocity. So let's just start down at the bottom there. As time passes, as I go to 1 second, it'll go up. Now, instead of saying it, I should rather say the displacement. So here we go. So as time passes, the displacement increases. As it passes again, it increases by the same amount. That's what it means to have constant velocity. The displacement will be going up in exactly the same step each time. So I hope that you can see how I got from my velocity time graph to my displacement time graph. Now here's a little bit of a challenge. I hope that you're drawing these as practice at home. So grade 11s, grade 12s could be watching this as well, because guys, this is something which comes up in your matric final. This is a matric section. So now it's very important that we understand exactly what's going on here. Now what I'm going to do is I'm going to talk about increasing velocity, something which is speeding up. Now it's usually easier to start with the one which we've got a description for, and that is my velocity. So my velocity, as time passes, is increasing. So let's get used to using the correct words. So as time passes, my velocity will increase. Now that's at a constant rate. So if I've got a straight line, that means there's a constant rate. So there we go. I've got a velocity which is increasing with time. Now I'm going to put a bit of a challenge to you guys. I'm going to ask you what the displacement versus time graph looks like. And you might say, oh, how am I meant to guess this? How do I remember the shape? Guys, we've got to understand what's actually going on. Now, I'm going to draw on my VT graph to find out. My velocity should be, and here's where it comes, my velocity should be a reflection of the gradient on my x versus t graph. Now, that's a lot of complicated language all in one sentence, so let's slow it down. If I find my velocity at a time, it should be the same as the gradient on the other graph. So at the moment, can you see that v versus t is sitting at 0? Let's just prove this. Let's highlight this. So my v versus t is sitting at 0. That means that the gradient on my x versus t should also be 0. What does a 0 gradient mean? That means a flat line. Ladies and gents, take a look at that. That is a flat line. There is no gradient. Now, as I move my v versus t upwards, can you see that the velocity is going up? The velocity is increasing. Therefore, on my x versus t, my gradient should be increasing. So let's do this. So I've got x versus t. So my gradient has got to increase. Now, think about this. A flat gradient looks like that. An increasing gradient gets steeper and steeper and steeper. So that's what should be happening to my x versus t graph. As velocity goes up, my gradient should be going up. Now let's draw it onto the graph there. So what I should find is that I get this beautiful gradient which starts out flat and ramps upwards. I should be getting an increasing gradient. Now just to test this out, you could draw in a couple of flat lines over there. So that's a 0 gradient as we started. But at the end over here, can you see that I've got a very steep gradient? That means that velocity has increased. The gradient on an x versus t graph should reflect on your velocity time graph. So let's just go through that again and make sure that people are okay with this. Let's just take through a couple of those pieces that people are a little bit confused about. So starting on my v versus t. Right at the beginning, I have no velocity. So on my x versus t, let's just highlight this. I should have no gradient. So 0 velocity, 0 gradient. Now, what happens as time passes? My velocity is going to increase, so my gradient should also increase. So drawing this together, so I should have an increasing gradient. The line should be getting steeper and steeper and steeper. That means that my object is traveling faster. So there we go. I can see a steeper gradient. And a steeper gradient on a displacement time graph means that my velocity is increased. Now let's describe my displacement versus time. My displacement versus time is increasing. So as time passes, displacement is increasing. But how is this different from the last graph which we drew? This one is increasing at an increasing rate. Now, increasing rate, guys, that's gradient. So over here, as time passes, the displacement, I must start with a description of the displacement because I'm looking at a displacement time graph. So the displacement increases at an increasing rate as time passes. Please make sure that you're using the correct words. Now, guys, I'm going to give you a little bit of a challenge. Before we go away for a break, I want you to try and draw in the graphs for decreasing velocity. So velocity which is getting less and less and less. And we're going to check back with you after a short ad break and see if you managed to draw the right graphs. What do you think? Time for a break?
It is time. And Mindsetters, you have some work to do over the break. And let me remind you also that from the 23rd to the 27th of September, we are going to be having our spring school. So be up and ready to learn more with us, because on that we'll be having live shows, we'll be having some revision and some exam tips and exam questions that are going to be treated by experts. So make sure that you don't miss out that one. More information will be on Facebook. Don't move. See you after the break. Welcome back, Mindsetters. Now, before the break, I told you about the spring school that we're going to be having. What we're doing now on Facebook is that we're posting some exam tips, which would like you guys to make sure that you grasp them, and you use them, such as this one, Phil. Tip number 16. It says, if you do not get the question right, try it again after a few days. We know that there are some Mindsetters who write the test today and then leave a question that you didn't understand and you got it wrong on the paper, and leave it. Just leave it like that. So the tip is, go over it. Even if you didn't get it right, still try it again after the test also. So that's it.
Absolutely, guys. It's try, and try again. Guys, all of the stuff you guys can do. I've never met a person that cannot actually do the stuff if they don't try hard enough. So if you can't do it, like he says, just leave it for a little while. If you're getting frustrated, stop, make a snack, go to sleep, come back, try it again.
Or just consult also. Ask your mates, did you get it right? I'm sure, someone would have the answer.
Absolutely, guys. Your friends are your resources. Your teachers are your resources. Your textbooks. Use your resources, guys. The best in the world are just the people that have correct resources and networking skills.
Yeah, true that.
Okay. All right. Well, guys, I gave you a little bit of a challenge before we left on the break. I wanted to see if you guys could deal with decreasing velocity. So for most of you, you kind of went, okay, decreasing velocity. Something is slowing down. Okay, so let's draw on the one that we know the most about. Now, we were told about velocity, so let's draw in velocity. So I know that velocity with time is decreasing in value. Now, here's just a little bit of a tip. Guys, your velocity time graphs will always be straight lines. Now, if you're working in high school, and you guys are, okay, velocity time graphs will never be curved. So if you're starting to draw curved lines on your VT graph, that's a sign that you're doing something wrong. Now, it's possible for them to be curved, but that's only at university level. So for school, we're starting to deal with velocity which just goes up, down, or stays the same, but always in a straight line. Now here, this is where we can have curved lines. Now, remember what I said, is that I can read my velocity and use my velocity to find out the gradient on my displacement time graph. So let's find out which part of this I'm actually dealing with. So I'm dealing with my velocity. My velocity starts out at a high value. A high value velocity means a very steep gradient. So let's start out there. I'll start out with a steep gradient. And what should happen to the gradient of my x versus t? My x versus t should get smaller. Sorry, I'm just busy losing it there. So there we go. It should get smaller and smaller and smaller as time passes. So I should start out at a high gradient and end off at a low gradient. Okay, so that's pretty useful. So what I'm going to do now is I'm going to start out at a high gradient, so heading up, and end out at a zero gradient, which is low. I hope that you can see what's going on in this graph. Is I'm starting out with a very steep gradient, so let's draw in a tangent to it to show the gradient. So a very steep gradient to show a very high velocity. Then right at the end, there we go. Right at the end, I can see a zero gradient because I've got zero velocity. So it's very important that you can be able to link these two up together. Okay, guys, now it's time to introduce you to the last type of graphs. And I'm pretty excited about it because most of you have already said, okay, well, increasing, decreasing velocity. Phil, you already taught me last week that a changing velocity is called acceleration. Okay, now before we move any further, I need to remind myself what the definition of acceleration is. Acceleration is the rate of change of velocity. It's how quickly I change my velocity from 1 meter per second to another meter per second. So now introducing these guys, let's start out just by dealing with some of these graphs. Now, I'm going to go back to my constant velocity graph, and I'm going to use that to draw an acceleration time graph. So now, instead of arranging the x versus t on the left, I'm going to put the v versus t over there, and we're going to draw it in. Remember what I said, a velocity time graph drawing for constant velocity, I should have the same velocity throughout. The whole time period, my velocity should stay the same. Doesn't matter when I start it. So I start out over there, and my velocity as time passes does not change. My velocity is always the same. Doesn't matter where I look on the line, that's telling me that I have constant velocity. Now, acceleration is the rate of change of velocity. Now you might say, well, how do I draw a graph if nothing changes? And that's actually your clue. Is there a change in my velocity? No, there is not. There is zero change in my velocity. So there's my clue. There is my hint for drawing in the second graph. So as time passes, the rate of change of velocity is 0. So I hope you can actually see what's going on here. There is no change in velocity as time passes. Let me just circle that and move left and right. So now as time passes, there is no rate of change of velocity. So my acceleration value is 0. It's 0. There was no change in velocity, so there is no acceleration. So as time passes, my velocity remains constant. As time passes, there is no acceleration or is 0 acceleration. So there's nothing happening in terms of a change in velocity. Something else I want to focus on is the unit of acceleration. Now, when you work with the unit of acceleration, there it is, meters per second per second. That's kind of strange. Why is it to the -2? Whereas velocity is to the -1. The big difference here is, I'm saying, how many meters per second did you change every second? So it's meters per second again. So meters per second. And that's where this 2 comes from. I'm dividing by time twice. I divide by time once to get to velocity. I divide by time again to get to acceleration. Okay, so I'm hoping you're on board. And I want to use this opportunity to start talking about increasing velocity. Because last week I told you that a change in velocity means that there is acceleration happening. So let's deal with an increasing velocity. Let's draw in a line for increasing velocity. Remember what I said. There is no curved VT graph in school physics. So if it's increasing, it's always increasing at a constant rate. What would my acceleration look like? Now, I know that there is a change in velocity as time passes. Is it a positive increase or a negative increase? Well, I can see that as time passes, my velocity is heading upwards. That is a positive slope. The rate of change on a VT graph is my acceleration. So my acceleration is constant and positive. So now acceleration just means that the whole time, as time passes, my velocity will increase at a constant rate. Now please, again, make sure that you are looking at the correct graph and you are using the y-axis in your description. So if I go to my left graph there, velocity time, as time passes, the velocity is increasing at a constant rate. For my acceleration time, as time passes, there is a constant positive acceleration. It does not change with time. Now, just to prove things, my acceleration is constant all the time. So as I go left and right, my acceleration is constant all the time. Which part on a VT graph should be constant? Well, guys, I hope you've been listening very carefully. It should be the gradient on a VT graph that should be constant the entire time. So my gradient on my V versus T graph should be constant the entire time. Now, let's deal with that very last situation I left you with. And that was one for decreasing velocity. So let's draw in the one which we've got information about, and that is decreasing velocity. So as time passes, my velocity decreases at a constant rate. Now that's not too difficult. We've drawn that one before. What would the acceleration time look like? Now, if you've been watching closely and listening very carefully, you'll notice that my velocity is decreasing with time. So my velocity is going down, 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 down at a constant rate. My change in velocity is better known as my acceleration. There is a negative change in velocity, so that means that there is a negative acceleration. Negative acceleration means that there is a negative change in my velocity. So guys, I'm hoping that you understand how these two graphs link up. The gradient on a VT graph is equal to my acceleration. So the gradient remains constant, my acceleration remains constant with time. So if you're wondering how this all links together, what I've decided to do is I'm going to try and use one graph. This is a really nice example, and I want us to draw the two graphs together. Now, we're going to start off with a graph which has got a vehicle which moves first from rest between time A and B. Its velocity increases, then stays the same between B and C, then decreases between parts C and D. So let's take this apart into very small segments. Okay, now first thing I'm going to do is describe what is happening between position A and position B. I would say that the velocity is increasing at a constant rate. Now what does that mean for my displacement time graph? My displacement time graph uses the gradient to reflect velocity. So how would I get my gradient of my x versus t to increase? A curved line. So A to B must be a curved line. So I can see that I'm linking this up. But wait a minute, I've seen this before because it's just one of the first graphs that I drew. Okay, so my gradient is increasing. But what about position B to C, where the velocity remains constant as time passes? I hope that you can see that that means that the gradient must remain constant. That means a straight line from B. Okay, so a straight line over here. And then what happens? All that I'm going to find is that when C to D happens, my velocity is going to decrease. Let's just make sure that this is nice and clean. We don't need that piece over there. Right, so what happens from position C all the way through to D is that my displacement continues to increase, but at a decreasing rate. Oh, that's a lot to take in. Because my velocity is going to decrease from C to D, my gradient must decrease on my x versus t graph. So it's going to increase at a decreasing rate. So my displacement will increase at a decreasing rate. I hope that you can see what happens when I transfer my v versus t to my x versus t information. I first accelerated up to position B. I continued from B to C at a constant velocity, so my rate of change of displacement remained the same. Then from C to D, my displacement increased, but at a decreasing rate. That meant that the velocity was decreasing. I hope that you can link up these two graphs and draw one from the other. Now, the acceleration time graph is actually one of the easier ones to be able to do. My acceleration time graph is something that I can draw relatively easily. Now, from position A to B, there's a constant increase in velocity. Now, that tells me that there's acceleration happening. It can't be zero. There is a change in velocity. So that means from position A to B, my velocity is going up. That means positive acceleration. Because my slope is positive on my VT graph, my acceleration, which is the slope, should also be positive. Okay, so that should be a positive acceleration. Now from position B to position C, there's no change in velocity. If there's no change in velocity, there's no acceleration. So here's how I continue my graph over there. Let's just make sure we make that nice and clean because you guys are making some notes off here. I'm hoping so. So starting there, right, there is no acceleration. I hope that you can see that we've included that there is no acceleration. Now I don't want to draw it directly on that zero line because then you can't see it. The question is, how do I continue my information if there's a break in the line? And this is where we draw in a dotted line. So dot, 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 dot. So starting at the top there, dot, 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 all the way down, and that links up the two pieces of information. And then next, what we've got from C to D is a negative slope, so therefore a negative acceleration. So I hope that you can see that that is going to slow things down a bit. So that means that when we draw on our dots over there, I'm going to have a negative acceleration. Okay, guys, that's about all we need to chat about in terms of the graphs. We can elaborate a little bit more when we come back from the break. And then we're going to summarize things, guys, and then we're going to start changing from graphs of motion into equations of motion in the second part of the session. I think it's time for a break, eh?
Here's a quick question before that break.
Good.
Tseho Onika says, are you saying that acceleration should always be a straight line?
Okay. Now this is a really nice tip. I'm glad that he noticed that. Acceleration, lucky for us, is also a straight line, and it's always a flat line. Our acceleration time graphs are always flat. It's either positive, 0, or negative, but an acceleration time graph will always be a flat line. Really nice. I'm glad he's noticing that.
All right. Well, if you're still confused, mindsetters, make sure that you go over Facebook. Our Facebook page is facebook.com/learnextra. Like the page, ask some questions. I see some other mindsetters also on the page. They are very much helpful, such as Daniel is also on the page. Join them and let's help one another. Team Mindset. Don't go. See you after the break. Welcome back, Mindsetters. Now let's look at what are you guys saying on our Facebook page. The first, we have a question firstly, Phil, from Elias Sipuru, which says, why is the acceleration not changing when the velocity changes? But also, I'd like us to first start with this one. Can you please repeat the last question? I didn't get the answer, which is posted by Tepo Span. That question, you still remember, it was why is acceleration, why should it always be a straight line? Okay, now acceleration, now we've got to remember what our definition of acceleration is. Acceleration means that velocity is changing. If I have an acceleration of 1 the whole time, that means that the velocity is changing by 1 meter per second every second that goes by. So now let's actually put some numbers on this. So if I put some numbers on here, let's say that my acceleration is positive 2. What that means is that my acceleration is 2 meters per second every second that goes by. So now to answer both of their questions at the same time, that value is going to remain the same. Guys, in high school physics, your acceleration will either be a positive value and stay the positive value, or it will be 0, so that means velocity is not changing, or it will be negative, but it'll always be a flat line. Now what this means is that my acceleration is the change in velocity for every second that goes by. So what does this number 2 actually mean? This number 2 means that my velocity will change by a number of 2 for every second that goes by. So my velocity will look like this. If I've got an acceleration of 2 the whole time, that means that I'll go 2, 4, 6, 8. Can you see that my velocity is going upwards? But my acceleration was 2 for every one of those seconds. So this value of 2 is the whole time. I can move this 2 around. This 2 is there. 2 is the whole way through. That means that it's 2 meters per second every second. So my velocity again will go 2, 4, 6, 8, 10, 12, the whole way. That means my velocity will increase by 2 meters per second every second. So I hope that answers your questions and makes things a little bit clearer. Guys, acceleration is one of the trickier ones because it's not directly related to any direct evidence that I can see. I can't say the object is moving at 2. What does 2 mean? 2 meters per second squared? Oh, that means that it's increasing its velocity by 2 meters per second every second that goes by. And that helps things a bit to put some numbers on. Cool. Right.
All right, well, we're going to get back into it.
Unless you want to take out the last one.
Absolutely. Let's take the last question.
Benita Wang says, is there a gradient of A versus T with a gradient of more than 0?
Oh, okay. Now, A versus T, because it's flat, will always have a 0 gradient in high school physics. Okay, now when you go out into university, you can start to get A versus T, which starts to get more than a 0 gradient, and then things start to get really, really complicated. Guys, that is actual rocket science. When you start to deal with rockets and acceleration of vehicles and whatnot, you can start to deal with acceleration time, which actually starts to increase and decrease. That's when you'll get curved VT graphs and things get a little bit confusing. So for the sake of high school science, we've dealt with A versus T, which has always got a 0 flat gradient. Really nice. Okay. All right. Now, to summarize things, what I've decided to do was to give a little bit of a summary as to how and why I'm drawing these things next to each other. Okay. Now, you'll notice that there's usually a graph which I described in the middle. It's probably the most useful one, and that's my velocity time graph. You'll notice that that's right in the middle of the summary. If I use the gradient of a v versus t graph, I can get my acceleration. Now that's really cool. If I use my gradient of my x versus t graph, I can get my velocity. So we've been using gradients all the time. Now there is a way to go back. Now if you divide by t to go towards the right of your screen, I can multiply by t and find the area underneath the graph. And that helps me go backwards. So let me just show you what I mean. If you took this graph over here and you found the area underneath each part, you could actually relate this to the displacement. So if you chop that up and found your area underneath there, what you would actually find is you would find the final displacement at position B. If you added the area of position BC, if you added that up, you would get your further displacement over here, and that would give you your final displacement. But if you find your gradients, you can go to acceleration. So that's going gradient. But you can go area to go back to your x versus t graph. It's really beautiful that you can move backwards and forwards from your v versus t graph. You can find your displacement and you can find your acceleration directly from your v versus t graph. This is one of the reasons that they usually give you a v versus t graph, because people can picture velocity a lot easier than they can picture acceleration or displacement. So that summary, guys, if you're busy frantically copying it down, guys, it is in our notes. This exact picture is in our notes, and I'm fairly sure it's already been posted.
Also in Facebook.
There we go, guys. It's up on Facebook, guys. You don't have to scribble this down. I just want you to understand that you can go backwards between all these graphs. So x versus t, if I find the gradient, I will find v. If I find the gradient of my v versus t, I can find my acceleration. Now, obviously, you can go backwards using the area, and that's one of the things that I'd like you to practice on. Now, out of all of these divisions of time and multiplications of time, what scientists have managed to do is said, instead of finding the gradients and areas, all of these things, what we can actually do is we can develop some shortcuts instead of finding areas all the time. And what they've come up with is these four beautiful equations. Now you might say, whoa, that looks like a lot of maths, Phil. Okay, guys, again, please, these equations you do not have to learn. Now, you might recognize some pieces out of these equations. Now, where have I seen a half times something times something? Guys, this actually comes from your graphs. A half times something is actually a way to find the area of a triangle. And this is one of the things. So displacement and displacement are found from the area of v versus t graphs. And that's where these first two left-hand equations come from. Now, you do not have to memorize all of these equations. What we do have to do is we have to know how to use them. So you've got to sit there with these equations next to you, ready to use them. They will always be given to you in an exam. In fact, these came directly from a final matric paper. You still use them all the way up to matric. They don't get any more difficult. But guys, you've got to brush up on your linear equation skills to make sure that you can deal with some of these variables inside here. Okay, so again, we do not need to remember them, but we need to know how to work with them. We need to know what the variables mean. Now, the best way of doing this is to get ourselves a problem-solving approach. Now, before we jump into our example, I've got a 4-step approach which I still use today. Guys, I am double your age, and I still use this approach. I've been using this approach longer than you guys have been alive. So now it says choose a positive direction. Now you might say, why? Phil, why are you doing this? And I thought this has got nothing to do with equation. And you can only see equations in the last step, guys. Preparation is success. I'm going to tell you now that these first 3 steps will get you absolutely no marks. However, if you don't do them, your equation will have no marks in it. You will get 0. So guys, preparation is everything. Always choose a positive direction. Then draw yourself a simple picture. I know that most of you guys are not artists, But you'll notice that I like drawing pictures, even though I'm not the greatest artist, but it helps me arrange my information. Then we tabulate my information. I make a table of what I have and what I still need to get. Then, and only then, do I get an equation. Now you might say, well, Phil, you told me not to memorize anything, and now there's 4 steps in front of me. Now it's very easy. If you write down these letters, it'll help you. D, D, T, E. This is the order in which I do. A direction, a diagram, a table, then an equation. Those are my 4 steps. D, D, T, E are my 4 steps. Diagram and direction are probably the most vital step of this. Only then can I decide which equation am I going to use, substitute, and find out. Best way to show you what's going on inside here, let's take a look at an example. A car accelerates from rest to 15 meters per second in 5 seconds. Now, we've got a lot of information, but we're not sure what we're being asked. Now, the first question wants us to calculate the acceleration over that time period. So they are looking for acceleration. Now, a lot of you are saying, okay, now I'm going to start shuffling my way through 4 equations. But you are leading this exploration. You're going in blind. Okay, so what I've got to do is arrange my information. And the best way to do that, get myself a little bit of empty space over there on my page and choose yourself a positive direction. So I'm going to choose the forward direction for my vehicle to be positive. So I'm going to draw in my car over there. So there's my car, and my car is coming over here. Right. So there is my car. Okay, it's a sports car, and it's going to accelerate forwards. So now this is just helping me visualize what's going on. Notice how it's not a beautiful car, but it gets the point across. Now let's start adding the information. It says that it starts from rest. So my V initial is 0 meters per second. Okay, that's nice. What else does it say? Well, it said that it accelerates from rest to a final velocity of 15 meters per second. So I know that when it's over here, I know that my V final is equal to 15 meters per second. All right, that's useful. I know that the entire trip takes 5 seconds. Now, beautifully over here, now all of a sudden I've got a picture inside my head. I know what all the information means. So that is the beauty of this. So what we're going to do now is we're going to calculate the acceleration using the correct equation. But we can only do that after we've done step 3, which is to tabulate. Now, there is a shortcut to be able to tabulate this. Now, I call it the VV tax table. So VV tax. So what I'm doing here is V initial, V final, my change in time, my acceleration, and my x. Obviously, that'll change if you're doing vertical stuff. Okay, so let's fill in what I have. My initial velocity was rest, so 0 meters per second. My final velocity, I knew it was velocity because it said meters per second, is positive 15 meters per second because I decided that forward was positive. Okay, my time is 5 seconds. My acceleration is the equation, or at least the unknown over here. Now guys, here's a bit of a trick. It's a little bit of a hint. After years and years and years of doing this, there is a little bit of a trick to finding the correct equation. Now, I've got my initial velocity, my final velocity, and my time. You need 3 variables to be able to do this. And I've got 3 over there. Now, I'm going to look for an equation which also has A, but before you waste your time, notice how I haven't talked about the displacement. I don't need it. I don't want it yet. So look for the equation which does not have displacement. Ah, okay. All right, now we're getting somewhere. The equation without displacement is far easier to look for than for looking for 4 variables. So look for the equation without displacements. So I'm going to help you. So putting those 4 equations in front of myself, immediately that means that I ignore those 2. I can see displacement as clear as day there. However, this one, and notice how quick that was. There's no displacement inside this equation. So that's beautiful. V final is equal to V initial plus A delta T. Let's use it. So we've done our tabulation. Now we've chosen an equation based on my tabulation. So there we go. V final is equal to V initial plus A delta t. So V final is positive 15. Now notice how I'm emphasizing the positive. It's heading forwards. Guys, these are vectors, and direction is shown by the sign. Plus means forward. So over here, V initial, 0, plus A times delta t. It took 5 seconds. Now, guys, please practice your skills when you are trying to manipulate this. So this leaves me with 15 is equal to 5 times delta t. To get delta t on its own, I divide both sides by 5. Please don't subtract it, that's incorrect. Divide both sides by 5, and what I'll get is that 3 is equal to delta t. So therefore, delta t is equal to 3 seconds. Now guys, one final warning. Always put a unit on your final answer or it's wrong. I can't say that it takes 3 minutes, 3 hours, 3 seconds. Okay? So, apologies. I've actually gone down the wrong path here. I hope you guys noticed. What I've written down here instead of delta t over here, we were actually after delta a. I hope you noticed that. I only noticed this now. Is that we were dealing with 5a, so 3 is equal to a, and a is equal to 3, and it's not seconds, guys. So please make sure that your units are correct. Now this is acceleration, so what is a unit for acceleration? I hope that you noticed from earlier on in the show, that is meters per second squared. But now there's still something missing from my acceleration. It's positive 3. Now acceleration used velocity, so that means that acceleration is also a vector. So vectors need a unit and they need a direction. So 3 meters per second squared, forward. Okay, so I hope you don't mind that little mistake, but the important thing is that you catch your mistakes. You won't ever stop making mistakes. Sadly, I still make them, you can see, but it's important that you go back and fix them, and you get better and better at that. Now let's answer our very last question. I think we've got a few minutes left. It says, calculate the displacement during this acceleration. Okay, now this is another point at which I'm going to tell you a really important tip. I now know what the acceleration is. I'm going to write it in. I know that I'm accelerating at 3 meters per second during that time. Now you might say, okay, well, yay, that helps me out. I can use acceleration. Guys, please don't use your acceleration because it's calculated. It could be wrong. So what I'm going to do is now I'm going to look for an equation without my acceleration. So without acceleration. So I'm looking for something with all the other equation pieces that I need. And without acceleration. And if you do this really quickly, I'm going to have to do this quite quickly because we're running out of time. Delta x is equal to vi plus vf over 2 times delta t. You'll notice that there's no acceleration anywhere inside here. So let's do this quickly. I know that v initial is 0 plus vf is positive 15. My time period is 5. And then I divide that all by 2. So now when I put this in my calculator, the really nice thing about our calculator, the Casio calculator, is that it can do fractions directly for us. So on top of this, I would say that I've got 0 plus 15, close my brackets, multiplied by 5. And what do I have to do to that answer? I have to divide it all by 2. There we go, and I get a displacement of 37,5, and that is my final answer. But I'm not out of the woods yet. I haven't done all my job yet. I need to give it a unit, displacement's measured in meters, and it's a vector, so it needs a direction of forward. So I hope you guys understand what I'm meaning by direction, drawing, tabulation, then equation. Guys, all of those steps are vital. The equation one gets you the marks, but the other ones prepare you to get those. I think that's all we got time for, guys.
Because of time, unfortunately. But I just want to urge all the mind sitters, if you know the answers and you can help other mind sitters, be on the page and let's help one another. Otherwise, you can also send us an email or go via our website for the help desk on www.mindset.co.za/learn/help desk. That's where we can help you. But otherwise, from us, we just want to say thank you very much, Great Hands, for tuning in. Learn more and learn extra. Keep up the focus. We know that this chapter is a bit difficult and challenging,
Absolutely.
but you can still crack it out because we are here to help you. Otherwise, peace.